Okay. All right. I try to give you these little mental salves, right? So we can. Really is weird about the sound, though. I don't know, like with the special things. Okay. All right. Okay. So hierarchical self-similar structures. Hierarchy is mixed. Tokunaga's law is this sort of beautiful thing underneath it, and we've got connections between them. And I'll give you a few problems so you can play around with these things. Anyway, yeah, and they're just like little sums and so on. You just be careful with them and kind of set them up right and so on. There's no, advanced measure theory or something ridiculous. It's counting stuff up. Yep. Combinatorics people, it's like just very easy. Okay, and then this took a while to get here, right? But we have this story now that there are only really two Horton laws, that they fit together in this nice way, and we had that equipartitioning thing, which I feel like is a bigger story that we just haven't quite told the world about. Okay, so it's true that sometimes it takes like at least 10 years to write a paper. It's just like it has to go fallow in your idiot head, and then eventually you figure it out. And it's good that it takes some papers infinity, because you should not write them. So, but it is a weird experience, to live long enough for that to happen. And the crucial thing about life is to date everything as a result. Presume you will be around and put a lot of things like this, right? 2018-01-25 thing. Really good later on. Really good. Okay. We could have a whole lecture about that. Okay, so only two parameters independent. So we end up with this kind of nice story that we just had this really clean thing from Tokunaga. This seemed to have 3 and originally even 4 parameters, but actually we got it back to 2, and we can go back and forth between them, even though this seems to imply and people sort of make mistakes about things because it looks like a pure hierarchy. The goodness is all in here. All right. So let's go back out to so there's another way to attack this, and I've mentioned this, which is we'll just get rid of the stream ordering thing for a while. It's very helpful to try and understand how things fit together. But we could just pick a random point, and then we'll ask, so some random point. It could be on the network, and I think that's the way it's structured. It could be just a point in space, but we'll ignore those. But so random point here. Of course, one thing that we've ignored in all of this is width, right? And maybe depth as well, but there are also other pieces. Obviously rivers get wider and deeper, and blood networks, they're thicker next to and that's a big piece we'll get to later, I suppose, but really just for blood networks. So we pick a random point, and then we look at the basin. So let's say it's this one, and there's some basin, right? We find the basin that drains into that point. What's its area, and what's the longest stream in there? And then, of course, you have things like the characteristic Euclidean shape of the thing, right? Length and width. So we can talk about now kind of a probability distribution, because we're randomly sampling from this network. What's the probability that it has a area A and an area length? So this is /E_L, which Dave Dewhurst is your he's the sort of assistant deliberator for this course. If I haven't mentioned that yet, I realize I should have. And he will be both your TA and grader and all those sorts of things. He's going to help out with office hours. He told me the other day that he's made every L that appears in any math thing that he writes in LaTeX look like this, which is well done. Anyway, so it's a nice L. This is what you get. You get a power law, and it's a to the minus tau and L to the minus gamma. We're using notations for those indices, for those exponents that you often see in the literature. Of course, people go and measure things from different places, and you see this is roughly the case, that the exponent, so this is a fatter tail, right? It's a smaller exponent, and we, of course, always write these in a way that, so we have a to the minus. This is a positive quantity, right? This is always a good way. Whenever you have any understanding that something will be positive or negative in here, you absolutely must indicate that. Anyway, so these numbers these are smaller than these numbers, which means on a log-log plot, the area distribution is going to have a shallower slope than the length one, which makes sense, right? Area is length squared, so bigger things. But But we'd like all these things to, so how does this fit together with the stream ordering thing, and how do these things fit together with each other? We've talked about these things in pucks a little bit. Okay, so we've talked a lot about these Powerlaw distributions, or at least heavy-tail distributions for probability distributions or frequency distributions for sizes, right? So, and they matter a lot. And so we sort of frame this as the statistics of surprise, right? So the normal distribution, yes?
For the drainage basin containing P, which drainage basin are you talking about?
Yeah, so you take, so you can rescope this, right? So we could, this could be one that's for a whole continent, or we could take a, you know, a particular basin and so on. And then, so it's going to keep working within. Yep. You know, and of course you don't go down to too small a point. But that's, that whole self-similar structure is, yeah. So you want a large enough one for which you've got enough samples and so on, yeah. And there's always this problem of, you know, the slopes are hard to measure and it's messy and all these sorts of things, but it's, you get these tails, it's pretty good. So something we haven't talked about, and I need to put this in somewhere properly, is these slopes can be hard to measure and these distributions can be hard to measure, but a very powerful thing is to look at these things at different scales, right? So we might take this basin and find its Powerlaw size distribution and then find a bigger basin and so on. And you'll see how and you put them on the same plot, you see how the larger scale cuts off, right? And then you can do some work which is called finite size scaling. So it's a big part of complex systems, right? I mean, lots of systems are made out of different, lots of little parts, and they have different sizes, whatever it is. I mean, for people, you know, we can think of our wealth as one aspect, or your number of followers on Twitter, which is apparently an important thing. Et cetera, right? And how many of those are bots? But, you know, you have different sizes for things. You know, for biology, you've got just the number of organisms of certain species, and they all have to fit together and so on, right? Okay. Growth mechanisms are very important, usually, in how these things get this way. And of course, you know, there's a clear growth thing that's happening with these networks. Optimization is at work as well, and we had that nice example from the MIT thing about piracy and so on. So there's you know, definitely a movement towards equilibrium of some sort. All right, so we want to get to the mechanism, and as I've said, it's not really there. There are lots of little growing models and so on, but I don't think there's a universal one. Okay, so we have this detailed picture of branching networks from Tokunaga, really. We'd like to derive these things, and so we're just going to set this up, right, for a couple of, for just the probability of length. See if we can go from this sort of detailed structure to this big story one. You know, and when you're getting out to these probabilities, you're just sort of randomly throwing darts at this thing, and you're not thinking about how things are connected together, right? So if you just have, if someone just gives you this distribution and a distribution for area, and then says, you know, make a network out of that, that's not going to be super easy, right? In fact, probably the easiest thing would be to make a pure hierarchy. All right, anyway, okay, so we're going to imagine that Horton's law is just what we sort of did for the area calculation, that they hold perfectly, right? Okay. And then we just do something like this, and we bite the stick, right? Okay, so and just sit down and sort of work through a calculation. So I'll give you the outline of that. It's nice to do these things. As we did in pucks, complementary cumulative distributions are always good things. Cumulative distributions appear everywhere in statistics, but often with these Powerlaw type ones, we want to look at the complementary one, which I'll use this kind of notation. So it's the probability that when you sample whatever it is, in this case length, that it's greater than some quantity, and we'll write that as length star. So that will be the probability length is greater than, so this is this notation. Here the little greater than, and so it's going to be whatever we have, a sum or an integral depending on our distribution, in this case up to L max. And for these distributions where we sort of think of them as going off to infinity, you know, we allow this to go to infinity, right? Okay, so complementary cumulative, it's going to be 1 minus the cumulative distribution. You'll see the words exceedance probability. We've talked about these things from some familiarity, remember these things. But the big deal for Powerlaw type distributions, and exponentials work as well in a useful way, is when you integrate a Powerlaw distribution, the exponent pops up by 1, right? So if we have a -4 Powerlaw, which is a pretty weird one, then we'd have a -3 for its complementary cumulative distribution. Integrating is smoothing, right? Differentiating is smashing things up a little bit, so integrating is smoothing, so we always get better things to look at, and statistics work better on them. So this has been a game that people have been happy to play for a long time. But as we showed the other day, people are still tweeting some shade at each other and writing papers of shade. Should have just thrown out that GIF, the one that has the shade coming across the buildings, that one. That's high quality. Like the little cloud that goes, and just says shade. I said GIF, right? Yeah. Okay. I come from a time of GIFs. Okay, so, all right. So this is the calculation, and I'm just putting it in here. We've done this a bazillion times. Out of the minus gamma is the character we're interested in. We do our integral. It's just the simplest little bit of integration that you can do. Right, so the exponent pops up by 1. We're framing this as minus a positive quantity. It's going to be minus a positive quantity again, so we keep our little minus sign out here because we're good people. This is, right, it's going to be small, right, out at L max, and so the minus sign here, we're going to have 0 minus this blob evaluated L star, so that cleans that guy up. So it's going to be proportional, as I said, to this L star quantity to minus, and the exponent will have decreased by 1. All right, so that's a good way to work with these kind of distributions for measurements, but it's also analytically useful. So we okay with this? Remember this little thing? Yeah. All right. Turn page. You can tell me to turn page. This is my oldest daughter when she was really little, right? So you're reading books and they have no idea what a book is, right? They just don't know, what are we doing? And but I remember realizing we're going to work on the mechanics of reading a book, which is, I mean, it depends on your language, right? But we're going to turn the page, and that's a big deal. So that was the first instruction. We would say things and read they're apparently eventually understood to be correlated with the words on the page, but the turn page part was a big deal, which I got her to do. And now she reads tweets. Or Tumblr. Wow, so great. Should never teach people to read. Okay, so, no, she's an incredibly smart person. So, yeah, it's just great moments for me. Okay, so let's see. So we're going to do this thing. So we're going to try to figure this out using our stream ordering. But we're not, because of stream ordering, it's pretty coarse, right? So we sort of know about these points like somewhere along this stream, we could be along this stream. We kind of, we have an idea of how everything works from a stream ordering point of view, so we can roughly do this. All right, so we're going to have some spatial resolution, this capital delta, and we're going to have a nice grid. So we'll kind of cut things up like that, which is also true of our data, so that's useful. And the idea will be we'll approximate this complementary cumulative distribution for length as the number of squares that we find that have, right? So we're going to have a grid on top of this, and then we're going to go to each grid point, and if it has a mainstream length, if we have a basin there that has a mainstream length greater than this L star, then we count it, and if it doesn't, we don't, and then we divide by the total number of boxes. Fine. Right? Okay, it's a bit of an odd thing to do, but this is fine. So we have Horton's ratios, Horton's laws, and we have in particular the one for stream segment lengths, right, which will tell us roughly how long this one is, and roughly how long this one is, and roughly how long this one is, and of course we know the number of them. Another Horton law. Okay, so we're going to say, let's just anchor our, I really don't have my stick. I must. let me find a stick. Such an important thing to be doing right now. Oh yes, here it is. I was going to use a pump. I could use a pump. No? Use a pump for a little bit. Okay, good. It's a very nice pump. So this is going to be, we're going to say we know about these guys, right? Because our little stream ordering thing works at these scales. So let's just say, let's start at some omega and take that length. Right, so we're just going to insert it in there, and this is the sort of crucial thing, right? So we're assuming Horton's laws work in this pure hierarchical sense. We've got a basin that goes up to some order, capital omega, this is 10 or whatever it is. This is going to be the total stream length, length of streams in the whole network, right? So what we're doing is, estimating it, because these are averages. We're going to add up, we've got all these streams of length 1, order 1. So we count all of those, and we multiply them by the average length, and we count all of the 2s, and we multiply them by their average length, and so on, so on, so on. And then we're just going to divide by this length scale, and that'll give us the number of boxes, roughly, right? So we're sort of fitting this little kind of a fractal story. It's going to give us roughly the number of boxes that we required to cover this whole network. And there are boxes in here that have nothing inside them, right? No network inside them. So we've done the right thing. And then we want to find then we want to count the number of boxes that cover parts of the network, where if we stand on that part of the network, then there's a basin that has a stream that has a mainstream length, right? If we travel up there, that's greater than this thing we're interested in. And the way that's going to work is, we just start this sum, so everything looks the same as this one, but we'll just start the sum at omega plus 1, right? So we're very sure that, not very sure, statistically at least, every point on let's say this is 3, an order 3 thing, then every point on an order 4, 5, 6, 7, 8 stream segment will have a longer mainstream length, right? It's in a bigger basin. It's in a basin of a higher order. What has happened?
Is this kind of like a generalized box counting?
Yeah, it's like box counting. Yeah. Yep. And we're fitting these little boxes. I mean, we're doing it at a bit of a, we just well, look, there's a grid behind it. So imagine this is a very fine grid. Yep. And then as we sort of make that grid finer and finer, we're going to have a bunch of little boxes that fit on this one.
But it's still like a probability because it's like just a number of boxes that are divided by.
So that kind of, so imagine, so you exactly have that view, right, of the number of boxes required to cover it. That's some scale. And of course, as we move that scales in an interesting way, right? That's the fractal story. But now we're going to do two things with it. We're going to have all the boxes required at some scale to cover it, and then we'll light up those boxes that cover the ones that are, right, exactly. So you can imagine like 2 of these pictures, and then you have all the boxes here, and then only the boxes that are covering, say, in this one, this one.
This is assuming that the streams have no width.
Yeah, or that we're not going down to such a small scale that it's, Yes, it is a crass and terrible thing to do, but it will work. So these are going to cancel out, right? Joink. Using the excellent package cancel, also canceling. And if you add up all of this stuff, right, as we showed before, this is basically the area of the whole thing, because we've added up all of the stream segment length, and if we multiply by a sort of a characteristic width of these things, then we've got the area of the whole basin. So that's really what's happened here. It's the area of the whole basin multiplied by the drainage density. Yeah. So, which is the inverse of this characteristic width. So total area divided by the characteristic width of around a stream would give you the length of all the streams added up. So this is just overall constant. And we're not making our boxes so small that it's not true, and they're not so grossly large that it's not true either. Okay. So using Horton's laws, or let's get this right. So really it's just the top piece, and we really just have this sum. The interesting thing now is that it's going to start at omega plus 1. It's going to go to this fixed capital omega, and then we just have to be a little thoughtful about how we do that again. It's again best to start with the fact that there is one stream of order capital omega, so then we can count backwards from that. Do the right thing. Yep. Yeah, right. So when this omega prime is capital omega, this is just 1. This is to the power of 0. So that's going to increase correctly as we go backwards. And we have some characteristic scale for the length of these first orders, and we can build up from there with the Horton's law for stream segment lengths. And really, these are the only things that matter. There's a little r sub omega here, and then this little character here. The rest are constants we can pull out. Yes. Well, not quite true. We have to be careful with this sum. So we always like having sums that start from 1 or 0 and go up to something. So that's what we're going to have to do, right? We're going to flip this upside down. Yes? You guys will work through this for area, so this will be a good point. So this is just what we had on the previous slide, so if you're still looking at that, that's okay. So as I said, we can throw a few things away. And this is really the interesting piece that's doing the scaling. And then the usual little business, we have to sit there and concentrate and worry about 1s and 0s and starting at the right bit. Yeah. But if we start with omega double prime, we're going to say that let that equal to omega minus omega prime. Then we're going to have a sum that'll start in a nice way and will go in this direction, and that'll be a better thing. All right, so I've got the things written down. So, okay, so when omega prime is capital omega, right, this sum goes from small omega, normal omega plus 1 to capital omega. So now we have 4 omegas. That's great. A capital 1, a basic 1, one with a prime, one with a double prime. I'm very sorry. So, but when this omega prime is capital omega, this is a 0. So we're going to have a 0 there. And when it's omega plus 1, we're going to put that in here. We're going to have capital omega minus little omega minus 1. And that's what's on this next line. So now we have a new sum. It's going to go from 0 up to here, which is fine. We like zeros to things. And we'll have to replace this piece here with our new character, which is, right, this is going to be, we have simply omega prime equals omega minus omega prime, and we'll just flip them around. So omega prime is omega minus this one, right? So we're going to take this, second line, and we're going to put this blob, that's where we write on the board, and we make a terrible mistake. We're going to put it here. This will be capital omega minus omega double prime. I wasn't at this, so someone was telling me years ago, there's I guess it was back in the day of having like overhead projectors and stuff, and this Russian guy had come through, and it's sort of a complicated, messy thing, but he's sort of out of his head a little bit, and he's doing the slides, and he sees there's a mistake, and he just goes at the board with the thing, and it's just projected onto a wall, and there's just like, and everyone in the audience apparently just went, no! The most drama you can imagine in a, anyway, just sort of attacks it, yeah. It's tempting, you get confused, like I guess I could be trying to do this, that would be, God. Okay, problems with magic rectangles. Okay, all right, so we're just fiddling around with things, we're just taking our time and making sure we, end up with something that looks like something we knew before, right? That's how humans operate a lot, that's right, yeah. We shortcut it a lot. It's like, that is what, I know this already, which is a terrible mistake usually. But we're getting it back to just a plain old geometric sum. So, but doink. This is what all of that does with our new omega double prime thing. So this is fine. It's a blob to some power, and it goes from 0 to a blob. So that's good. It's a geometric sum. We can also get rid of, again, this is now a constant that we're not worried about, so we could throw that out. It's really just the omega double prime, and we're going to flip this upside down because it's always good to have a positive power. And we know, generally speaking, this is sort of 4/2, so we have a sense that this is greater than 1. That's important. So it's growing. This is a growing sum. So it's going to be dominated by the upper term. And whatever this is 0 to something. So the sum is going to be dominated by the something to plus 1. So capital omega minus 1 plus 1 gives us that power. Okay, so that's a lot of messing around, flipping around with things. Again, we've got a capital omega. We don't really worry about that. The dominant piece in here is going to be just these ratios to this. This is our variable, right? Right. We're interested in what's the probability that it's greater than a particular length. We've been able to at least connect a typical length of the order omega streams to order omega. This is not quite finished, right? Because we need to express this in terms of L omega. So there's one last little sneaky thing to do. This is the geometric sum story here. Okay, so there's no out of control math, but it's just like being careful with things. Yeah. Obviously, you make horrible mistakes, and then you clean it all up and pretend that never happened. Yeah. Because math. Okay. All right, so just think about this for a second. We have to somehow we need to get this back in there. And what we know is, let me write it here. These things. We know that L omega is scaling as RL, right, to the omega. This is the Horton's law. It's growing in that way, right? The typical size, and good, which is RS omega, right? So this is the stream segments. This is the length of the basin, the mainstream length in the basin. Words. Okay. So what do we want to do? So this is how they're connected. So we've got a blob to some power over there. So there's different ways to think about this. You could just say, let's take omega out of this, right? Take logs, right? So we could have ln of r omega like this. This is, of course, some constant. So we'd have to be a little bit careful about that. Plus, and this is like behaves like this. Plus omega ln of RL to the omega, and I'll put S's. Boop, boop, boop. Okay, so we could do that. And then we have an omega, and we could play around with it. Just stick it in. All right, well, let's try it. We'll do it in a slightly different way. So not a bad way to do this is to... So there are different ways to smudge this around to get the right thing. So we could take whatever... This is blob to a minus omega. That's... we can always write that as... whatever blob, we can always write a blob as e to the log of that blob. So that's what this is. Yes. And this is our story here. We need to express the right-hand side in terms of this typical scale here. Yeah. And so we know this is how it's growing. It's growing from some typical length for the first order streams. And so we can do the same little game here. This is sort of avoiding taking those logs back there. It's proportional to this, so it's e to the omega ln of r and s. So it's almost like this. Okay, and I'm sorry, I have to jump onto another page. Okay, so what we're going to do, okay, so we have L of omega is equal to this blob. Okay, so we just need to kind of make that thing exist. So let's do that. This is what we've gotten from our calculation, and we're simply going to put an L omega in there and divide by ln of rs over here. right? So that ln of rs over here, this guy divides by this, it gets back to E omega, and then we're just back to this structure here. Yeah? But we've noted that this thing is our L omega. So now we have L omega to some power. And if we play around with this a little bit, this is ln of Rn divided by Rs, so that's ln of Rn minus ln of Rs, right? Log behavior. So that's what this is. So a couple of things will cancel. This one's going to cancel here and here. So we're going to end up with the typical length scale for an order omega basin for the mainstream length. It's going to be to that raised to the power of minus this ratio of logs plus 1. This is a complementary cumulative distribution, right? That's what we were aiming for. So in fact, we've identified it very nicely, right? So this piece here is gamma. Okay, so I know this was just some like working through some math, but it's kind of nice that it all ties together, and you can see now that this is odd, right? We don't even for simple random network models, we don't really have values for these guys. But we know that they actually will connect. I mean, we don't have analytic values, we can estimate them. Log of, in this case, the number, and then log of the number ratio and the length ratio involved. Okay, so I'm sure you're thrilled about this, right? So you can do this. You can do a similar thing with the area calculation. So probability of area, decay is a to the minus tau. And you play around with all of that. And eventually, actually, you see it's 2 minus 1 over gamma. So they're connected to each other, which is nice. So you see this is the scaling relation story where we have different scaling laws, but they are connected. So this took, decades for people of measuring these things separately to start to see that actually they kind of looked, or they, if you look across basins, there was sort of a similarity to them, and toy models have this connection as well, even if they have nothing really to do with real networks. So scaling relations, very nice. And then we'll do one last one, which is Hack's law, and we can do this pretty quickly. So this is this length to power is proportional to area to the h. We can use Horton's laws again, so this won't take as long. This is how length grows, and this is how area grows, and we're going to identify it as, we're going to put the number ratio in there straight away. So you can just do this sort of thing. Length is growing as same kind of manipulation. Instead of just rs to the omega, we're going to make it e to the log, right? And then we'll create an area piece in here. We want this. This is e to the log n of Rn, so this is really just Rn to the omega, so this is going to be our area piece. And to make that, we would need to divide through by ln of Rn, right? So that would get rid of this piece, and we'd be back to here. So we're just sort of building it out because we think they're connected to each other. Right, and then this collapses back, as I said, to Rn to the omega. This is some blob. This is, of course, the scaling of area to the omega. So that's our story. This is the average stream length is growing like this with area. There's some scaling here, scaling exponent, and that's going to be this Hack's law exponent. So we can do this one page. Right. So again, it's that same ratio appearing again. So that leads us to, how am I doing? That leads us to starting to see that a lot of these things are collapsing, can be derived from the same thing. And in fact, this is a good plot. All right, so